This is an interesting problem. This is Newton's law of cooling, and we're going to apply it to some forensics here. We're going to look at calculating how long it's been since someone died. All right, so first we have to get there, right? What do we have? The rate of heat loss by a body is proportional to the surface area of the body, S. Okay, and we know the T body, we know T surroundings. We're looking for the time of death. Temperature difference is going to be T minus T surround. All right, so that's what we're proportional to. We have a convection coefficient H, right? And that's proportionality constant. And so we have to relate the loss of heat to temperature change and derive differential equation of the body. All right. Okay. Here is where we're going to start. We're going to start with our initial statement, dq dt. The rate of heat lost is proportional to H, or is equal to HS T minus TS. Right, and TS is my shortcut for T surroundings. S is the surface area of the body. H is the convection coefficient for air. The other thing we know dq is equal to mc dt, right? So that from the heat capacity or specific heat, dq is mc dt. And so we can change this to mc, we're just substituting into the first one, mc dt equals minus hs onto t minus t sub s. Now, I'm going to change variables a little bit here because it's going to make it easier to solve this differential equation and set up the initial conditions. I'm going to say we have a function y of t that is equal to just t minus t sub s. All right. If I do that, if I just stick in y, well, take that out. Y is t minus ts. I can put y in right here in that dt. Y, the derivative of a constant, is 0. And so this differential equation becomes mc dy dt equals minus hs y. It's going to be a little easier to get to a solution. I'm going to isolate dy dt is minus hs over mc onto y. Let's call k is hs over mc. So we can write this as dy dt is minus ky. Now we know the solution to this. Y as a function of time is y naught, its initial temperature, our initial value, e to the minus kt. So we've got that. Again, what is y? Y is t at whatever time minus ts. What is y naught at t equal to 0? Well, that's t of the body minus t of the surroundings onto e to the minus kt. Now we have this nice little equation. T of t is t of the surroundings plus t of the body minus t of the surroundings times this decaying exponential, which makes complete sense, right? This is eventually going away, leaving with just t of the surroundings. But when we put t equals 0, we end up with t of the body, right? That makes complete sense. And so we've got our equation here for temperature as a function of time. Let's see how many of these things all right, write an expression of time constant of cooling in terms of specific heat, capacity, density. Okay, so time constant of cooling is 1 over k. We'll call it tau. Is 1 over k, is going to be MC over HS. M, in terms of density and volume, this is going to be rho V C over HS. And this is the time constant of cooling because this kind of sets the time structure for when things are going to cool, right? The larger this is, the smaller K is, right? The larger this is, the longer it takes for the body to cool. The smaller this is, the faster the body cools. And so in the last bit here, two bodies, same shape but different sizes, right? Which will cool faster. Well, same shape but different sizes. So the volume goes up for both of them. Our volume of one is greater than the other. What does that say about its surface area? Because density doesn't change. Specific heat doesn't change. Air doesn't change. Well, larger volume over surface. What's the relationship between volumes and surface areas typically? Suppose we modeled a person as a cylinder. Right? Suppose we model a person as a cylinder. The volume of a cylinder is pi times the radius of the cylinder squared times the height. That's the height. That's the volume of a cylinder. What's the surface area of a cylinder? The surface area of a cylinder is pi r squared, squared times 2, so that's the surface of both end caps, right? Plus 2 pi r times, that's the circumference, 2 pi r times the height. Well, which one of these grows faster as you make the body bigger? Right? If we were to say the height is the same, they have to have the same shape, so the height has to be proportional to the radius, right? Which is growing faster? Well, right, if the height is proportional to the radius, then the volume goes as the radius cubed, but the surface area only goes as the radius squared. So the volume increases faster than the surface area as you increase in size, which means tau for something that's larger but the same shape is going to be lower. And so a large person, the exactly same shape as a small person, will take longer to cool. So now let's look at the problem. Now that you've got all of this, right, you've got the actual problem. You've got this person, it's an 80 kilogram man. You know their surface area is about 0.7 square meters. The ambient temperature is 20 degrees. You measure the body temperature at 28 C. Take the specific heat of water to be 4184 joules per kilogram Kelvin, convection coefficient of air to be 4 watts per meter squared Kelvin, and presume the standard body temperature of a human is 37 degrees centigrade. How many minutes before you examine the body did he die? All right? How many minutes before you examine the body did he die? Well, if you go down here to this equation, you know everything in this equation but time, right? You know everything but time. So you've got to solve this equation for time. And good luck with solving this problem.